Tonight, we are going to be hearing from Dr. Scott Kenyon from the Harvard-Smithsonian Center for Astrophysics. Dr. Kenyon will be presenting a talk tonight called Pluto's Revenge. He received his BS in physics from Arizona State and his master's and doctoral degrees in astronomy from the University of Illinois Champaign-Urbana. He's a fellow of the American Association for the Advancement of Science and the American Physical Society. And his awards include, but are not limited to, the Hoops Prize and the Copernicus Medal. His current research interests include solar system formation, a study of debris disks to infer outcomes of planet formation, and using hypervelocity stars as a mechanism for assessing Milky Way matter distribution. So, Dr. Kenyon, it's all yours. Let's hear about Pluto's revenge.
Well, thank you very much for that gracious introduction, Edward. It's a pleasure to be with you in some way or another. I will share my screen and ouch. Yes, so sorry for all that song and dance, but thank you for your patience. And it's a pleasure to be with you. So you've all heard of the contention over whether Pluto is a planet or not. And today's talk is about Pluto's redemption. So in 1915, Percival Lowell, building on the successful discovery of Neptune, used the motions of Neptune and Uranus to predict another planet beyond the orbit of Neptune. And people started searching for it. And unlike Neptune, where it only took a year or two to find the planet pretty close to its predicted position, it took 15 years to discover Pluto. They took lots and lots of plates of the sky, photographic plates of the sky, looking for something that moved. And eventually, Clyde Tombaugh discovered a moving object, and it was eventually named Pluto. It was not exactly what Percival Lowell predicted. He expected another gas giant like Neptune or Uranus. Pluto was about 2.5 or so magnitudes fainter than expected. And after a few years, they figured out that it has a very strange orbit compared to the other planets. All the other major planets, including the asteroid belt, orbit in a plane known as the ecliptic. And Pluto has a very eccentric orbit, eccentricity about 0.25, much more eccentric than any of the other 8 interior planets. And the orbit is inclined at about 15 degrees or so to the ecliptic plane. So that was all unexpected, and people were very disappointed that it didn't seem to be another gas giant. In 1978, Christie noticed on photographic plates of Pluto that it had a little blip on one side of it. And he thought that was a little odd, but a few days later, the blip appeared on the other side. And a few days after that, it appeared back on the first side. And so after many plates, he realized that it had a period of around 6.4 days. And he named it Charon. It was clearly a moon of Pluto. And so now Pluto was pretty interesting. It had a binary companion, and based on the photographic plates, it was a pretty big companion, roughly half the size of Pluto. And that, again, there was a long period where nothing really happened to Pluto. People observed it, they discovered it sort of had an atmosphere, not much of an atmosphere. But in the early 90s, when CCD cameras became generally available for astronomy, people started to look, deeper into the outer solar system to try to find other objects that might be either orbiting with Pluto or orbiting beyond Pluto. And Jane Liu and Dave Jewett found the first one. You can see the little arrow pointing at the object, and you can see that it, relative to the background stars and galaxies, that it moves. And it moves at a speed that puts it at about the same orbit as Pluto, give or take, although this orbit happens to be circular. Over the next decade, there were many of these discoveries. There's Eris, which also has a little moon next to it. Pluto and Charon, Makemake, Haumea with several moons, Sedna farther out in the solar system, Orcus, Quaoar, Varuna, and so on down the line. And so, these objects all inhabit about the same orbit around the sun. This is a top view of the sun, the solar system. The sun is at the center, the little yellow ball. The white circle is Jupiter. The magenta circle or ellipse is Saturn, and then green is Uranus, blue is Neptune. The cyan ellipse is the orbit of Pluto. You can see it goes inside the orbit of Neptune and then goes far away. And then all these other cyan dots are the positions of other objects in roughly the same orbit as Pluto, or at least in the same distance from the sun as Pluto. And these came to be known as Kuiper belt objects, named after Gerard Kuiper, who had predicted that there would be some things beyond the orbit of Neptune. In addition to objects that have fairly circular orbits around the sun, there are a bunch of objects that have orbits like this magenta ellipse, very elliptical orbits that approach the orbit of Neptune, but have very large distances from the sun at perihelion. And there were so many of these, people started to argue about, well, do we call all of these that are roughly the same size as Pluto planets? Or do we call them something else? And you probably know there was a big, to-do with the International Astronomical Union, and both sides had their reasons for thinking that Pluto is a planet or is a dwarf planet, much like the sun being a dwarf star. For some reason, things got very emotional, and eventually Pluto was demoted. Here's a set of orbits looking from the side of the solar system. So we're in the plane of the ecliptic. So all the little magenta ellipses are here. Here's the orbit of Pluto, this ellipse, the cyan ellipse. And here are the instantaneous positions of a bunch of Kuiper belt objects. Some, as you can see, are in the ecliptic plane. Others, if you can see my arrow, are well out of the ecliptic plane, like Pluto. What's interesting about Pluto and the other ones, the half a dozen or so on this plot that have very elliptical orbits, is these objects are in what we call a resonance with Neptune. And a resonance means that the orbit of Pluto is an integer or half integer multiple of the orbital period of Neptune. And in this case, Neptune takes 3 orbits around the sun for every 2 of Pluto. And so that means that, and Pluto is locked in this position for as long as Neptune doesn't move around any. And so Pluto will take its 2 orbits while Neptune takes 3. And the advantage of that is that when Neptune's orbit when Pluto is inside Neptune's orbit, Neptune is not there. It's always on the other side of the solar system so that it doesn't collide with Pluto. So because there were so many of these objects, Pluto got demoted. And here we have a little graphic where the 8 interior planets, Jupiter, Saturn, etc., are looking at scans at poor Pluto, who's been demoted. And in the public, it caused a lot of consternation. This is a graphic, an image from a movie theater where they, instead of having movies, they want Pluto to be a planet again. There were lots of demonstrations. All we are saying is give Pluto a chance. And the battle goes on today. And I'm not going to get any more involved in it other than to begin sort of the rehabilitation of Pluto as an interesting object. And it doesn't really matter whether it's a planet or a dwarf planet or something else. As Gertrude Stein said, a rose is a rose is a rose. And Pluto is one of the roses of the solar system. And Pluto's comeback started in the planning for the New Horizons satellite mission to Pluto. The New Horizons team wanted to make sure that the Pluto-Charon were alone, and so that they, so they would know where to guide the spacecraft as they made their flyby past the binary. And so they took a lot of HST images, Hubble Space Telescope images, and you can see two of the images here. The big bright star-like thing with the diffraction spikes is Pluto. The little fainter one is somewhat fainter one is Charon. And you can see two little dots to the right below the rightmost diffraction spike. And they have many of these images. And so they took a lot of these images and they found that these little dots orbited Pluto and Charon a little farther out. And one is named Nix and one is named Hydra. And I'll show you a little bit more about those as we go on. And so these images were taken in 2006. They kept taking images and they didn't find anything. They took more images and they didn't find anything. But finally, they did find two more satellites. And here's a composite of several of their images. So you have Pluto at the center, Charon below left. These orbits are schematic. They're obviously not on the image. And then the innermost moon is Styx. The next outermost moon is Nix. And then there's Kerberos to the right and Hydra to the left. You can see that Nix and Hydra are a lot brighter than Styx and Kerberos. Styx is about as faint as the Hubble Space Telescope can image something orbiting the Pluto-Charon system. And so, they had these four objects. And because there were four objects, those of us who do planet formation and moon formation models worried that there was probably more material between Styx and Hydra that you can't see here, really small things. And so instead of going through the moon system, which they might have done had they not known about these, they decided to have an orbit or a flyby that went between Pluto and Charon. And they did that. So this is an artist conception of the New Horizons satellite. And it passed by Pluto, 6 or 7 years ago, and it found a lot of amazing things. So this is one of the images of Pluto. And you can see craters, you can see things that look like similar to lunar Mara. You can see, valleys and rills and bright spots and dim spots. And no one really expected, Pluto to have much on it aside from craters. And they especially didn't expect to see flowing ice. These mountain-like things that you see here are made of frozen nitrogen. And you can't have frozen nitrogen on the Earth, it's too warm, but Pluto is a very cold planet, around 40 degrees Kelvin or so. And so these are essentially moving glaciers of frozen nitrogen ice. And here's Charon. Charon has a very deep valley, like the Grand Canyon. And this is this region, the depth of the canyon here, relative to the radius of Charon, is bigger than the Grand Canyon relative to the radius of the Earth. So it's a very big structure. And you see, again, dark spots, bright spots, craters. You can see them on the terminator here, a bunch of craters. You can see craters all around. And here's a schematic of Charon and the small moons of Pluto. They managed to get images of all four moons. Nix and Styx were actually the closest to the flyby as the satellite went through the system. So there's a pretty good image of Styx. Styx is really small, so there's not such a great image. Kerberos was farther away, but even so, you can see that it has two lobes. And Hydra was also far away from the flyby compared to Nix. And so its image is a little blurrier, but you can still see that it's a sort of a football shaped thing. And they're all about 10 to 20 miles across, give or take. Nix and Hydra being about twice to 3 times the radius of Kerberos and Styx. So while they were getting these images of the satellites, they were also getting images of the environment around Pluto and Charon. And they realized that after analyzing the images in detail, that there wasn't actually any small dust in the system that they could detect. And they did not find any new satellites inside the orbit of Hydra. Their limit was around 2 kilometers. So if there were a bunch of 1 kilometer satellites, they wouldn't have been able to see them. But anything larger than 2 kilometers inside or around, maybe a little outside, but inside the orbit of Hydra, they would have seen, and there was nothing. And they don't know any of the, because it's just a flyby, they have no idea what they have an idea, but they don't know what the real masses are. So that is my sort of prelude to what the system is like. And my colleague Ben Bromley and I have been doing various studies of the system to try to understand how it was formed, what its structure is, what its architecture is, how stable it is, and things like that. And I will describe a few of those things now. So before I do that, I just want to give you a schematic of the architecture of the system. So this is looking from the top. So you're looking down on Pluto and Charon and the satellites. And so they orbit in the plane of the figure. They go, in more or less circular orbits around. So Charon doesn't orbit Pluto, it orbits the center of mass, which sits outside of Pluto. So unlike the Earth-Moon system, where the center of mass is inside the Earth, the center of mass of Pluto and Charon is outside Pluto. Not a lot outside Pluto, but outside Pluto. And so it is a true binary, like a binary star. Because it's a binary, there's a region orbiting where things could orbit Pluto and Charon, but those orbits are unstable. So if you think about the sun, it's a single star. So aside from being too close to the sun and burning up, every circular orbit around the sun, or even many elliptical orbits, as long as they don't get too close to the sun, are stable. There isn't an unstable region around the sun where moons, satellites, planets can't orbit. But in Pluto and Charon, the binary creates an interesting gravitational force where this region in white here is unstable. That is, if you place a satellite, a moon, and you make sure it's not going to hit Pluto or Charon, the gravity of Pluto and Charon will perturb its orbit, and it will develop a more eccentric orbit, and that eccentricity will grow with time. And eventually it crosses the orbit of Charon, and Pluto and Charon eject it. Gravity is a funny thing. You think that gravity only pulls things in, but gravity can also push things out if the dynamics are right. And so this region is unstable. And the orbit of this gray region is what we call the satellite zone, where amazingly enough, the satellites are. And Styx is almost at this unstable region. So it's about as close to the unstable region as it can be and still have a stable orbit. And then the orbits of Nix, Kerberos, and Hydra on their way out. All of these orbits are pretty amazing, actually. They're essentially circular, very small eccentricities, 0.01 or 0.02 or less. And they're all within a degree of the same orbital plane as Pluto and Charon. So that gives you an idea of the system architecture. And one of the questions that we're interested in is, are there other satellites in the system, small ones, since New Horizons didn't find any larger than 2 kilometers? And if there were satellites, where would they be? So the way we do that is we do what's called an n-body calculation, where we put Pluto and Charon on their orbits. We know their orbit very well. And we put the satellite on their orbits, and we do a computer calculation where we follow those orbits in time. And we can also put massless particles in orbit around Pluto and Charon, and we can watch them. And we follow these orbits for millions of years in system time. And fortunately, that only doesn't take millions of years in human time. It takes a few weeks or so. And we can find the possible locations of new satellites in the system. So here is a starting condition that we tried. We've tried several of these. This is the initial state of the system. This big dot at the white dot at the center is Pluto. The smaller one is Charon. These two objects will not move. That's an artificial thing, but I didn't want you to get dizzy having Pluto zip around there. And then these orange dots are the four satellites. And then all these green dots are massless particles that are given circular orbits around the system, around the center of mass near Pluto. And so if they find stable orbits, they will sit there for millions of years. And if those orbits are not stable, they will be ejected. So here I will show the movie. And so the movie is not a continuous movie, it's a set of snapshots. So you'll see how the system evolves. And you can sort of adjust to see the time will be in the upper right, and you'll see how the moons go away, potentials. So after 100 years, you can see that the system has changed. Some of the satellites have gone away. And as time goes on, it only takes a few thousand years to start to clear out the orbits. And what happens there is the gravity of the four satellites moves the small massless particles around, and eventually those particles get too close to Pluto and Charon eject them into the solar system. Or in the case of our computer simulation, they just eject them from the simulation. So after after 10 million years, you can see that I'll play this again in a second, but you can see that the system has been pretty well cleared out. There's a stable region just inside the orbit of Styx, around the orbits of Nix, Kerberos, and Hydra. There's very few stable orbits, and those will go away over another 10 million years or so. And then outside the orbit of Hydra, there is a very nice stable region where there are a lot of particles survived for 10 million years. We suspect that this inner region inside the orbit of Styx, which is in between the edge of the unstable zone and Styx, that those will probably would go away if we wanted to run the calculation for 1 billion years. But it didn't seem like that was worthwhile. What's interesting to us is that there's a lot of satellites that could exist outside the orbit of Hydra. And so the other project that I'd like to tell you about today is how the satellites came to be. They have this amazing architecture, as I said. Pluto and Charon have a circular orbit. They have a day that's equal to their orbital period. So like the moon, Charon has the same face towards Pluto all the time. It's just that in Pluto-Charon, the day of six and a half days for Pluto and Charon is equal to the orbital period. So the moon orbits the Earth every 30 days, 29 days, and the Earth has a 1 day period. And so they're not tidally locked in that way, but Pluto and Charon are. And we have these four satellites, as I said, that have nearly circular orbits and have orbits that are essentially in the same orbital plane as Pluto and Charon. So to understand how Pluto and Charon and the 4 satellites came to be, we have to understand the origin of the solar system. And our current ideas about the origin of the solar system go like this, that 4.5 billion years ago, all the material and the planets and the sun were in a giant cloud, thousands of astronomical units across. And that cloud had a little bit of rotation and it collapsed because it had enough mass so that the gravity overcame the pressure in the cloud and it could collapse. And it collapsed into a protostar at the center. This is the proto-sun, or at least an artist vision of the proto-sun. And surrounding the proto-sun was a big disk. And that disk extended, well beyond the orbit of Neptune. And material continues to fall on the disk as things go on, as the evolution continues. And the planets form rather like the dust bunnies under your bed. There's a lot of dust in this disk, and it gloms together like the dust bunnies under your bed. And after 2 or 3 weeks, you notice a pretty big dust bunny under the bed if you have nice wood floors. But you can imagine how big it would get if you have millions or tens of millions of years. And so that's what happens in the solar system. You have some dust grains glom together and they make bigger dust grains, and those bigger dust grains glom together and they get bigger and bigger and bigger until eventually they make a planet. And so in this swirling disk, we make the Earth, we make Jupiter, we make Pluto, and we make Charon. And the theory these days is that Pluto and Charon were made separately. And the satellites formed from a giant impact or a large impact. And so the idea for the giant impact model is rather like the collision that makes the Earth and the Moon. And I'll show you a picture of that. It looks like this. So the idea for the Earth and the Moon is that a Mars mass planet came along and it hit the Earth and embedded itself in the Earth. And that, energy that it put into the Earth ejected a small amount orbiting the Earth. And that small amount glommed together to make the Moon. In the impact that makes Pluto and Charon, we want to make a binary and a closer binary. And so the idea is that there's a more glancing impact. So here in the upper right, we have Charon, the proto-Charon. In the lower left, we have Pluto. And Charon comes from the lower right of the image, and it has a glancing collision with Pluto, and it goes on. And as it collides, it loses some energy, and it takes up an orbit around Pluto. And you can see that this collision kicks up some material. And that material might become the satellites. The other option is that that material is not enough to make the satellites, but later, after Pluto and Charon, settle down in their orbit, what we call a trans-Neptunian object or a Kuiper belt object, they're sort of interchangeable, collides with Charon, and the debris from that collision kicks up enough material, and then that material collects together into the 4 satellites. So what we do is we do a numerical simulation of what happens to the debris that gets kicked up from one of these collisions, either from something hitting Charon or something hitting Pluto. And so there's some debris. The debris has a certain amount of mass, and we follow the evolution of that mass in the computer code, and we follow how it evolves in orbit and how the particles evolve in size. So after the collision, the debris, which is shown in the orange ellipses, has orbits that look like these long ellipses. So the white circle is the orbit of Pluto. It goes around like this. Charon is orbiting the center of mass, but it's lower mass, so it's farther away. It has this elliptical orbit. And the debris has even more elliptical orbits. So the debris, from Charon would hit Charon if it could, and it goes out and it comes back, but Charon moves. And there are two, physical processes that happen in this kind of calculation or this kind of evolution. First, because the material in its closest approach of Charon is in this unstable zone surrounding the binary wants to eject it. But there's a lot of mass and collisions between the particles on intersecting orbits slows them down, and it tends to circularize their orbits farther away from Pluto and Charon, which would make them safe. So there's this competition between Pluto and Charon trying to eject things and the collisions of the small particles in orbit, trying to get their orbits circularized and to see if they can find stable orbits. So here's our simulation. The big dot at the center is Pluto. The dot to the right of it, just inside the mass of magenta and cyan, is Charon. And then we have all these particles that we follow. The magenta part close to Pluto and Charon is denser. So in the calculations, magenta signifies a larger density. The cyan, you can see individual particles out here, and that's lower density. So this is our initial conditions. All of these are on very elliptical orbits that would intersect the orbit of Charon. So I'll show you a movie and we'll see how it goes. So it doesn't take long for things to happen. This is, the time is in the upper right corner. After 3/10 of a day, you can see there's a little wiggle on the inner edge of the system. That wiggle gets bigger and bigger. And so after 7 days, there are sort of spiral arms. After 1/10 of a year, there are rings. Material is being ejected through these rings. And after a year or so, things start to settle down. And you can see that there's a ring far away from Charon. And as time goes on, that ring expands a little bit. But by 25 years, which is not long in Pluto-Charon time, you have a stable ring. And we'll play this again. So it starts out with nice, it looks like a circle, but it's not really. But you can see there's a wave on the inner edge of this ring, and it's starting to move away some. Some of the material moves closer and closer to Charon, and that material gets ejected. And so any material that looks like it's getting closer to Charon gets ejected. And then we have these spiral arms, which gravity likes to make, rings, which gravity also likes to make. And eventually there's just a ring of material. And so after 25 years or so, there's a stable ring of stuff. And it's all, the objects are maybe 1 centimeter to 1 meter across. And then, this is where we stop the simulation because this ring is stable. And our next simulation is to try to see if the satellites can get made in this ring. This particular ring is midway between the orbits of Kerberos and Nix. So it's a little bigger ring than we'd want. And so we're going to try different initial conditions, mostly the mass of the material, to see if we can get a somewhat more compact ring where the material could glom together the way where planets and moons get made in the solar system to make the 4 moons. So the next steps in our probe of the Pluto-Charon system, I'll start with the second one, since JWST is doing such a marvelous job of giving the public images and giving the scientists some new things to think about. It turns out that moons the size of 1/2 kilometer so would be visible with images taken by JWST, and there is a program by the New Horizons team to get those kinds of images. So it may be that in a year or 2 or maybe 3, depending on when those observations get scheduled, that the Webb telescope will be able to find moons in the system that are unknown at present. And Ben and I, having done these calculations, are hoping that whatever new moons they find are in the regions we think they're supposed to be in. The other step in our ongoing saga with Pluto-Charon is to try to understand in whether or not in these disks or rings that are made from these impacts, whether the satellites can grow and whether we can make 4 of them that have the sizes of the Pluto and Charon moons, of Styx, Nix, Kerberos, and Hydra, whether they have the orbits and the sizes. So thanks for your attention. I hope I've convinced you that Pluto is a really interesting planet or dwarf planet, no matter what you want to call it. And the cartoon character Pluto is very happy that Pluto is a really interesting system, regardless of what you call it. And thanks for your attention. And I'm happy to take questions.
Do you have any questions?
Ed, put the light on. Top one.
Yeah, thank you very much. That was very interesting. And my question is about your first N-body modeling. When you put in the 4 satellites and distributed bodies around, and you ended up with the 2 rings. My question is there an analogy between what happens there with what might have happened in the solar system, that the first ring of particles would be analogous to the asteroid belt and the other to the Kuiper belt? If you put the Earth in the center, or the sun in the center, and then instead of Charon, you had the 4 rocky planets, and then you had the 4 gaseous giants, and ran the same kind of modeling, would you get a similar result?
Well, yes, it's not. It's since the sun is a single object as opposed to Pluto-Charon being a binary, it's not quite analogous, but it is similar because if I'll go back to the movie because I can. So in the movie, well, I won't go back to. You can see that the regions around each of the small satellites from Styx to Hydra get cleared out pretty rapidly. And that's what happens in the solar system. So the region between, of Mercury's orbit and the, along Venus's orbit, along Earth's orbit, along Mars's orbit, and so on, those have been cleared, and they're cleared in exactly the same way that the gravity of the planet pushes stuff away. And what, gravity doesn't really push. What happens is material gets close to the Earth. And as it gets close to the Earth, it gets a higher velocity. So when it goes away, it has a higher velocity than it came in with. And that tends over time to push it away from the Earth. And so the Earth, as after it was formed, 100 million years after the sun was formed, clears out its own orbit. And Jupiter clears out its orbit too. The asteroid belt is a special, and the Kuiper belt are special things, because the asteroid belt is near Jupiter, and Jupiter's gravity controls the asteroid belt. And so if you look at the asteroid belt, there are regions that are evacuated, and that's because Jupiter's gravity clears those regions of material. There are other regions that are safe from Jupiter's gravity, and so those are where the asteroids are. And in the Kuiper belt, I described to you, how Pluto is in this 2 to 3 resonance with Neptune. And so these objects are captured by Neptune into this resonance, and they sit there. And Neptune clears out everything in Pluto's orbits in Pluto's orbit and other Pluto objects, Pluto-like objects are in the same orbit or roughly the same orbit. It clears out all the ones that aren't in this 3 to 2 resonance. So this clearing that you saw in the movie happens everywhere in the solar system and in other planetary systems, where the gravity of a planet clears out its orbit. And the bigger the planet is, the bigger the region it can clear out.
Anyone else? Yes.
Is there anything we know or have a reasonable guess to know about the core of Pluto? How that composed?
Well, it's generally thought that what happens in Pluto and the Earth and other planets that are big enough is that radioactive elements like uranium and other similar, elements, they're radioactive, they decay, that puts heat into the planet. And if that element decays on the surface of the Earth or the surface of Pluto, the heat, which is actually high energy photons, can escape. And so it doesn't really heat up much of anything. But in the core, those high energy photons can't go anywhere. They hit another atom or something. And so they heat up the core slowly. So over 1 billion years, if I remember correctly, Pluto's core gradually heats up and melts. And then over the next few billion years, it cools off. So based on what New Horizons was able to learn, the core of Pluto, say the inner few hundred kilometers, is probably frozen now, but it's mostly rock or rock ice. And as you go farther and farther out, it's icier and icier and icier. And the surface is water ice, nitrogen ice, methane ice, ammonia ice, frozen things with very little rock. And that's similar to the Earth, where it's denser in the core of the Earth than in the mantle and the surface where we live. It's 2 or 3 times denser in the core than on the surface. That's probably true in Pluto too, that the density of Pluto overall is around 2 grams per cubic centimeter, which is less than rock on the Earth, but more than water. But the core is much denser than that, and the surface is, the density of water, more or less 1 gram per cubic centimeter.
Anyone else? In the back?
Has Pluto always been in its current position from the sun, or is there any evidence for migration from the inner solar system?
It's believed that Pluto formed around 20 astronomical units from the sun, close to where Uranus is now. At the time Pluto was formed, Uranus was closer in also. So Pluto and Charon formed at around this 20 astronomical units, or the 20 times the Earth-Sun distance. And then Pluto and Charon collided. And then the 4 giant planets expanded their orbits. Jupiter stayed put, but the orbit of Uranus and Neptune moved out. And as they moved out, they captured Pluto into this 3-to-2 resonance. So it started at 20 to 25 Earth-Sun distances, and then moved out to its current 40 because Neptune was moving out, and it was captured by Neptune, so it had nowhere to go.
Anybody else?
The large heart-shaped planar area, do they have an explanation of how that forms?
I couldn't quite hear that.
The heart-shaped region that's very visible, and if there are
Oh, yeah. I'm not really a geologist, so what I know is pretty simple. But my understanding is that that's a fairly flat, smooth region that doesn't have, where the nitrogen ice is more lake-like, if you want to call it that, than having these mountains. And it probably formed, because what happens with Pluto is that depending on Pluto's orbit, the nitrogen sublimates, and so it makes an atmosphere. And then when Pluto gets further away from the sun, it recondenses. And so this cycle happens, every Pluto year, which is 200 some years long. So that process, changes the surface of Pluto over time. And that's about all I can explain, because the geologist could do that much better than I can.
Yeah, we have a question over here.
Yeah, I have a question on the computer simulation over millions of years. I'm just wondering, is that a supercomputer or many body problem used, or many cluster computers?
So, well, we use a NASA supercomputer called Discover, which is operated by the National Center of Climate Simulations. So whatever the climate simulation folks don't use, we can grab up some of that time. And so it's the way the simulation works is that when we have the 4 satellites in Pluto and Charon, they react to the gravity of the 6 objects in that group. And then we have these massless particles, which we call tracers, which were the green dots in the simulation. And those react to the gravity of the 6 objects that are orbiting the center of mass. And those tracer particles do not impact the motions of the 6 more massive objects.
Okay, anybody on Zoom that wants to ask a question?
No Zoom question.
Okay, right, so we're all set then. Well, Scott, thank you so much. It was a great talk, greatly appreciated.
Well, it was my pleasure.
Yeah, no, the Pluto is clearly a pretty interesting system. So I'll be in touch, with you and Margaret to set up a meeting time, and we'll get on with those things. And again, thank you so much.
Well, thank you very much. And if anyone has other questions, please feel free to email me. Edward can give you my email if you have a question, and I'll respond as soon as I can.
Thank you very much. Greatly appreciate it.
Thank you.
Okay, well, thanks a lot, everybody. Have a good evening.
You too.
Thank you.